Hey, what's going on? I'm still working on this case for vectors. So I've already given you the abstract case where I've gone through and I've told you the reasons why we need vectors. But now I'd like to start with my example. And my example is going to be a simple example. It's just going to be gravitational attraction between two objects. But it's going to be an example that I can do in both a Cartesian coordinate system and with complex numbers. They're really the same thing, but that's part of the point, right? And the same thing with vectors as we go on. So I'd like to talk about this in terms of the Cartesian coordinate system first, and just go through and show the way things actually worked out. And you'll notice when I go through and work it again later that a lot of the forms will return, right? The same ideas show up over and over again. It's just the way that we have to proceed is a little bit different. And in particular, when we're trying to work this gravitational attraction problem, without the vectors, without the complex numbers in this case, you have to use your brain. All right, you have to think about everything and try to make sure everything works out and is in the right place, the right time, and so forth and so on. That's one of the things that all these mathematical techniques give you, as well as being able to work a lot of problems quickly. The mathematics contains within it a lot of reasoning, and so you don't have to use your brain to reason through the same thing over and over and over again, because the vectors just in their nature, the complex numbers as well in their nature, just solve a lot of problems by just being there for you, right? And if you can manipulate these things in their native environment rather than going down to components all the time, then you can actually do a lot of work without having it be meaningful only in one circumstance, or knowing that it's meaningful in more than one circumstance, because you haven't made any decisions about coordinate systems or anything like that. Whereas if I'm going to do something with gravitational attraction without them, then I will have to do it. So what I want to do with this particular problem is I want to take this idea of how much force does the moon feel from the Earth and look at that using different coordinate systems, all right? And I'm going to have two different coordinate systems in both of these cases, and they're going to be the same too, but first I'll just use the Cartesian coordinate systems with these coordinates. And so I'll first go through and show what they are with the Cartesian coordinates, and then I'll go through with the complex numbers, and I'll show that these two systems, these two ways of doing things, yield the same result. And in the case of complex numbers later on, I'll go through with some rotations and translations explicitly, right? So I can showing you that I can do the rotations and the translations without having to worry about anything as far as the components are concerned. And then when I go to the components after I do the rotations and translations, everything's hunky-dory, right? Everything is exactly the way it's supposed to be. So that's where I want to go and go with this, right? So I've got these two objects here. I want to lay down some coordinate systems. The first coordinate system will be directed from the Earth to the moon, right? Which means that I've got a one-dimensional problem. I've got the central force is a one-dimensional problem if something's not moving, and I'm not at this point caring about what the moon is doing. I just care about how much force is going on. So we've really got a one-dimensional problem, which is nice because I can just lay a coordinate system down from the center of the Earth here through the center of the moon, and then everything I can just measure from there. So this distance dE, it's just going to be dE in the x direction and so forth and so on. Or dME, excuse me, is what I wrote. And so there's no y force because it's a central force. And the gravitational force is going to be just its normal sort of thing that you learned in Physics 1, minus the gravitational constant times the product of the masses divided by the square of the distance, right in this x direction. That's all you need to do. There's nothing more complicated than that, right? And the minus sign just means rather than being from here to here, it's pointing back along the opposite direction of that arrow. That's all that's going on. Very simple to write that down. having chosen the correct coordinate system. We don't always have the options, however, of choosing the coordinate system like that, right? We might have, for some other reason, to use, say, just the picture as it's drawn here and use the coordinates from the box, right? So if we say we've got a point here and we want to measure from that point, this point in the lower left-hand corner, then we have to use these coordinates, right? I've made no special assumptions at this point. This is perfectly fine. We could do the same thing with our vectors or our complex numbers. In fact, we will. Only when we do that with the complex numbers and so forth, it's actually going to be a little bit easier for us to manipulate things. So now we've got this other coordinate system, and we want to figure out what the force is. Well, we still have the same magnitude, and if we think about it in terms of this angle, in terms of trig, it's fairly simple to figure out. We've got like cosine theta coming back this way, and we have sine theta coming up this way, right? That's the way we normally do things. It's simple trigonometry, fairly straightforward, but normally when we want to do something like this, we want to actually do it in terms of the coordinates we're using. So I've introduced a second coordinate system here. Actually, I've got two coordinates here that are not quite right? This DME has nothing to do with the coordinates here. That has to do with the coordinates here. It's the distance between here and here. So we want to substitute that distance, and we also want to substitute for that angle to something that's actually in this coordinate system, something that we measure, rather than something that at this point is now just a shorthand, right? It has nothing to do with the coordinates that we're measuring. It's just a shorthand. We don't really know anything about it. So we have to give positions to these things. We just measure them the way we measured them in the last video. X is coming straight down here. Y is going straight over here. Hunky-dory. And so then we make our nice little triangle, which, because of the Pythagorean theorem, now we have an expression for DME, right? And so, we have a DME squared here, a DME squared there, and we can substitute. Now we need to get rid of that theta. And trig comes to our rescue again. Remember all that fun stuff with I'm not sure how to do it. I don't want to do the SOHCAHTOA thing, but yeah, you remember all that SOHCAHTOA stuff, right? You can figure out, this is the sine, so it's the ratio of this side length, which is the difference between the y coordinates, and it's the ratio of that difference to the length of this hypotenuse, and so forth and so on. And there we have sine and cosine. We've got the cosine in this case. That's the ka part adjacent over hypotenuse, right? So we go and we put that in there. And we do the same thing with the sine, put that in, and here we have our expressions. I'm going to bet that I'm going to collapse these. I've forgotten. It's been a little while. I throw all that stuff in together into a smaller region, but that's how we have to do it. We have gone through and we've done this geometrical reasoning, this trigonometrical reasoning, and we've gotten some idea about what we need. But this is all through reasoning, right? It's nothing automatic, right? We'd like to be able to do something automatic. And in fact, when we go and use the complex numbers in the next video, we'll be able to do something automatic. It'll just all pop out. All of this stuff will pop out of the mathematics, and we'll be done. And it'll be nice and happy. And I believe that this is going to be the shortest of these 3 videos, because that is all I really want to do. All right? So try to keep that in mind. We've gone through and we've put these things all together. Now we're going to try to do it again, but this time with the complex numbers. All right? So I'll see you then. All right? Bye now.